In this paper, we introduce SparsePoser, a novel deep learning-based architecture that can reconstruct full-body poses, using only 6 tracking devices, with rotational and positional information. Our method encodes sensor data and a static representation of the user, and decodes it to a full-body pose by reconstructing all joints between the end effectors. We also introduce a learned inverse kinematics step that can accurately reposition the end effectors according to the sensor's information. Motion capture is a powerful tool for capturing and reproducing human movement, but commercial systems have several limitations such as high cost, a large number of sensors required, and difficulty in calibration. With the growing demand for interactive gaming consoles in Metaverse and other social platforms, low-cost systems that perform well in large and dynamic environments are essential. Current virtual reality systems commonly use 6 sensors to provide positional and rotational information, and run an inverse kinematics solution to synthesize full-body poses, but the resulting poses are often unnatural and without time coherency. Other works use a sparse set of IMU to reconstruct the full-body pose with deep learning models like bidirectional recurrent neural networks. Nonetheless, IMU suffers positional drift over time and cannot deliver high end effector accuracy or correct avatar placement in the virtual environment. Our method addresses these issues by using accurate positional and rotational data from 6 trackers, and using a convolutional-based autoencoder and a learned inverse kinematics step to produce high-quality and accurate human poses. Our pipeline includes a convolutional-based autoencoder that extracts main features from the sensor data and reconstructs the user poses for a set of contiguous frames. This step uses skeleton-aware operations to ensure continuity and high-quality human poses. However, we found that the convolution-based structure of the generator struggles to maintain the actual position of the skeleton end effectors. To solve this, we propose a learned inverse kinematics solution that consists of a set of feed-forward neural networks, each specialized in a specific body limb. The resulting motion better preserves the high-frequency details of the input, and can accurately position the end effectors. Once trained, our method can be executed using standard commercial virtual reality systems such as the HTC Vive, that provide rotational and positional information. We include a quick calibration step at the beginning of the application to easily calculate the offsets between the sensors and their related joints. We conducted an ablation study to evaluate the contribution of each element of our network to the overall performance of our system. Please refer to our supplementary materials for more details. We conduct quantitative comparisons against previous work for reconstructing human poses from a sparse set of sensors. Root Motion's final IK is the state-of-the-art inverse kinematics for animating full-body VR avatars when having a sparse set of trackers with positional and rotational information. SparsePoser introduce a conditional transformer decoder to reconstruct full-body poses. We extended it to work with 6 trackers for a fair comparison. We also compare our method against state-of-the-art data-driven methods that reconstruct full-body poses from IMU sensors, transpose and physical inertial poser. Final IK can track end effectors effectively, but struggles to synthesize natural poses and often introduces jittering artifacts. SparsePoser fails to synthesize some poses and does not accurately position the end effectors. Transpose and PIP, since they use IMU sensors, can achieve high overall pose quality, but they introduce positional error and low end effector accuracy. Although IMU sensors provide less information than trackers with positional and rotational information, we include them in the evaluation to provide a broader context for assessing our overall performance gains. Our method is able to accurately represent all types of motion while preserving pose quality, achieving high end effector accuracy and avoiding root drift. Here, we compare transpose, PIP, SparsePoser and final IK with our method when executed in real time. Note that the root is fixed for easy pose comparison. To evaluate the effectiveness of our method in reconstructing the motion of users with different body shapes and sizes, we show the reconstruction of motions captured with an X-Sense device from two users with distinct physical characteristics. Thank you for your attention.